Hello everyone and welcome. Thank you for joining us for the SANS Analyst webcast titled Critical Control System Vulnerabilities Demonstrated and What to Do About Them. This is our fourth webcast in our SCADA security series. I am Alex Bass with the SANS Institute and I will be moderating this webcast. Today's featured speakers are Matthew Luallen. He is the co-founder and president of CYBATI and adjunct faculty member at DePaul University, and Eric Knapp, Director of Critical Infrastructure Markets at Nitrosecurity. Before I turn things over to Matthew, the Q&A portion will take place near the end of the webcast. To submit your questions at any time, please use the chat window. Right now, I'd like to introduce our first featured speaker, Matthew Luallen. Matthew, would you like to take over?
Great, thank you very much, and welcome everybody that's here for the webinar. First and foremost, I want to let everybody know that we're going to be covering a lot of information pretty quickly and recognize that you're going to be able to follow up with this webinar, a white paper that we're releasing that's associated with it. Essentially, what you're going to see today is about a year's worth of work, one, being able to develop a hands-on training environment, and then secondarily to be able to facilitate that training environment within an educational platform such as DePaul University. And it was really interesting to see how the students were able to really learn about control systems and also vulnerabilities. So I wanted to set the stage as far as what we're going to talk about today, and I'll reference that as we continue on. So that said, we're going to start very, very briefly talking about control system architecture, which will give guidance as to why we selected or what type of training environment was selected to facilitate the students through. I know many of you have already worked in this type of space, so this may just be a bit of rehashing of what you already know. We're then going to go through some open source intelligence, essentially that the students found. As interesting as that is, there's a lot of information out there, and really, and maybe many of you have already seen this, but during the summertime, a video was released of one of my training classes from DePaul, going through and expressing some of the vulnerabilities they were able to find in specific types of PLCs, and we'll talk to that, but we'll also be going through what kind of information they were able to find out on the internet with very little facilitation from myself in being able to guide them down the path of what tools. A lot of it they found themselves. We'll then go through what this training kit looks like that they used, which will then be able to allow us to do this type of demonstration of some attacks and recognize, when we use the word attack, I mean these vulnerabilities specifically are what I would categorize as implementation vulnerabilities. Not a vulnerability directly with a vendor, specifically, not a vulnerability directly with, an application level challenge. They are going to be implementation vulnerabilities. So where that would match up with is what Marty Edwards has been associating with a feature of the environment, not necessarily a vulnerability. I think that that's a bit of a challenge, as you'll see when we go through these examples, that if my students are able to do these types of attacks, you have to make certain that you have the correct implementation, which will then lead into recommended security analysis and controls, then following up with some discussion from Eric Knapp on some good things you can do from a security, information, and event management posturing. So when we talk about control system architecture, I mean, the reality is the reason we've had such success in greater performance as well as reduced costs in the manufacturing market is because of technology and automation. It's because of the widgets that we put in place to be able to replace people and implementing our processes that people once did with technology. And, as we look at it, a person before, we had our senses, our 5 senses, and then we will understand the environment based upon those senses, and then we'll act upon that understanding. And that's exactly what we've been doing with embedded devices within controllers, within our control system servers, and then long-haul SCADA. And the reality is we've been automating technology by building some of this logic into widgets. And one of those primary widgets, as became overemphasized, not overemphasized, but became emphasized last summer of 2010 with Stuxnet, and further identified or reviewed with Dooku here recently, is the PLC and how it's programmed and how it actually interprets this logic. There's a lot of detail around this, and in fact, again, I recommend going through the white paper at length, because it even references presentations from Jason Larson back at Black Hat in 2008, and breakage analysis and being able to create water hammers or destroy high-speed rotational equipment. But the point is PLCs provide the programming logic, and typically multiple PLCs in an environment, controlling different aspects and functions. And on the left-hand side, it talks about the inputs, which would be our senses, and then the ladder logic in the middle, or functional block diagrams, however you'd like to be able to craft it, but in this case showing a specific RS logic application with this ladder logic being programmed, being our knowledge, and then on the right-hand side being our actuators, the actual acting process of our outputs. So this allows us to automate the environment, similar to, again, how a human processes information. And that's the analysis between the two that we really wanted to be able to show. Now, the PLC, of course, is just one component throughout the architecture, but it can represent a number of these capabilities, whether it's acting as an RTU or an MTU, a meter reading device. I mean, it can be programmed to do lots of different capabilities, and in fact, those capabilities typically are now being put into PLCs. They may also act as safety components, and typically are, and even programmed. The same PLC may be doing automation that's doing safety. So there's lots of components, but when we get to what we facilitated with our students at DePaul University and with the kit that was built, we focused in on an HMI or an OPC server, a PLC, and a communications channel, which really gets to the nuts and bolts of what control systems are about. You can then make it be long haul by having communication protocols that can allow for, again, remote control and supervisory control such as SCADA. But the nuts and bolts of an environment are going to be PLCs, HMI, and OPC servers. Then you can go further to look at additional automation and web front ends and additional remote control and historians. But we wanted to facilitate it around just that area to begin with. So let's get into some of the findings and from an open source intelligence standpoint. And what happened, and you'll see in the full white paper more details around this, we actually only selected 4 critical infrastructures from the National Infrastructure Protection Plan for the purposes of this white paper. But the reality is, I assigned to my students over 50 different areas within the 18 critical infrastructures. And this includes whether it's NOAA weather buoys or even weapons control systems or airplanes and ships. Those have all been assigned, but for the purposes of this paper and this presentation, we're focusing in on agriculture and food, transportation, water and wastewater, and physical and plant facilities from a physical security standpoint. Recognizing that we left out of this specifically the energy sector, and that was purposely to show, we've been hammering on that sector for a multitude of, now years, and we want to show that there's vulnerabilities in other areas. And what I asked of my students was for them to go and research search engines, vendor websites, social websites, control system user forums, use resources like ShodanHQ and eRIP once you want to find out if any of these systems happen to be directly on the internet or slightly off of it. And it was really quite amazing how quickly my students were able to become aware of what control system environments are by the hands-on environment that we'll discuss here in a moment, as well as just the right search queries and what they're able to find out on the internet, openly accessible. And again, recognize that the way that I was able to run this course was really from a facilitator standpoint. So what that means is I really wanted to copy somewhat of the discoveries that took place at Idaho National Laboratory and the Aurora vulnerability. If, I want to take somebody that hasn't touched a control system, and in fact, being students, many of them were even cybersecurity novices, and just facilitate them down the path of finding specific implementation vulnerabilities as well as open source intelligence. So without further ado, what were some of the things they found? Well, the first one here I find really most interesting. In fact, it's the most recent finding in the white paper because it just happened just in September. So we added this in while we were still in the draft stages of the paper. But essentially it impacts the food and beverage industry and specifically refrigeration units for the Carroll Plant Visor application. And this spurs directly off of Luigi's set of, what was it, I think 20-some vulnerabilities that he identified and released on September 13th. Oddly enough, the very first assignment that I had for my students this quarter, so I have active students right now this quarter that they're going to be coming out of my class in 2 weeks. They were to just look around out on the internet for all the things that I've been talking about in the control system, cybersecurity, and operational security domains, and find acronyms. I've just given them so much information over 2 weeks. Are they lost? Can they figure out what I'm talking about? Can they discover any type of good resources on the internet that would help them learn more about the space? And oddly enough, one of my students found a blog posting that was written in Spanish, used Google Translation to decipher the blog posting. It was written on September 20th with the title of All Your Yogurts Belong to Us. And it was talking about a refrigeration unit that was actually on the internet live right then, and then potentially, actually not just potentially, but the real steps based upon Luigi's notification on how to compromise the system, and even using this directory traversal attack, download the SAM password file directly off the Windows machine. So my student, who was a novice, read this blog entry that was written by a novice on how to potentially do this attack and successfully perform it. That is a bar-lowering event like none other from my standpoint of a novice documenting the vulnerability, finding a system live on the internet. And right now, as of November 1st, yesterday, there are still over 250 of these vulnerable systems on the internet right now. And you could potentially, well, you can change the temperature level of these refrigeration units and potentially taint the food supply chain within Europe. So right now, there are 5 countries these systems are located in, not including the United States. We did notify the ICS CERT over a month ago. We have gone through the process. Evidently, Carroll Plant Visor is supposed to be notifying all of their customers. But, the reality is, what's their incentive to notify their customers? So right now, there's still 250 of these vulnerable systems online. But the bar-lowering understanding of students finding these vulnerabilities being documented by another novice just trying to see how easy this attack is like no other bar-lowering event as far as the type of knowledge that it takes to perform these types of attacks. Another segment we looked at, and I gave to a student, was passenger automobiles, which could fall within the transportation critical infrastructure. And this student happened to find a series of white papers discussing well, in this case, a white paper that just came out in August, the Comprehensive Experimental Analysis of Automotive Attack Surfaces. And what this paper is going through, these 2 universities, University of California, San Diego, and University of Washington, is looking at potential injects to the tire pressure monitoring system, which is wireless, which operates at 300 megahertz, as well as additional injects of a Trojan song on a CD that actually compromises the control system of the automobile. Since many new automobiles actually pass through the CAN bus control network communication protocol through the car radio, as well as attack vectors within the Bluetooth connectivity capability. So pointedly, it's definitely worthwhile for you to read this white paper, and it goes back to actually comments that I made 1.5 years ago and I continue to make, that I strongly believe that the most amount of research in the control system vulnerability as well as protective space is most likely going to occur within the passenger automobile sector because it's easy to purchase a control system that's completed. All you have to do is buy a car and you can be impacting 5 million, 6 million automobiles on the road that have that exact same architecture. You're not going to necessarily be able to stand up a full power plant or stand up a full manufacturing line at the same cost. So we're seeing it, and it's going to continue to be a research domain over the coming months and years. Another category that was looked at was specifically freshwater and wastewater critical infrastructure, which impacts, from a dependency standpoint, many critical infrastructures. Because if you don't have water, then there are real challenges as far as how do you stand up a power plant without water? How do you have a good manufacturing facility without fresh water? And essentially, one of the students found open source intelligence, again, on the EPA's website, specific training scenarios, 2 out of 5 of them talking about cyber attacks, and specifically detailing the type of attack of impacting the high lift pumps and becoming also employed by the facility or a current employee and doing rogue changes. So, I find it excellent that these training exercises exist. However, the concern that the student raised, that actually I agree with, is specifically the roadmap that could be provided by us detailing the specific attack scenarios that somebody could take. Students found it. It was a great way to look. I mean, essentially, they looked at who the organization is that's in charge of the freshwater wastewater sector, being the EPA, from the NIT plan, and then mapped the website and found this training documentation, which you could do a search on Google right now and pull up. I mean, it is a concern. As the point is, actually, I was at a conference just this last week. When we deal with control systems, we're not dealing with PII, personal identifiable information. We're dealing with PLL. So you can hear this new acronym coined right here, potential loss of life, and that's my concern. That essentially we reached a critical moment around late summer last year that myself and many other people thought that it was prudent to develop this training environment, to develop this course at DePaul, and really strike the realization of how easy these types of attacks may be performed if given certain types of access or information. And that's the alarming level that we're at right now. I'll actually give another little note that based upon some search criteria that I just figured out last week, specifically in the freshwater, wastewater critical infrastructure, it is to go and do a search engine query for computer glitch water. And if you go and look around there, you'll find several different small towns throughout the United States that have actually had their full water towers emptied late last year and even the year prior, but a lot more between September and December of last year, where oddly enough they had false sensor readings, and all of a sudden the water towers dumped themselves. So that's not in the paper, but you can just do a search for computer glitch water and find a lot of information out there. The next piece of student findings was around physical facilities and physical security systems. And this was based upon a white paper that one of my students found that from Newman, Rad, and Strux. And in fact, John Strux is the, as I just met him last week physically, he is the individual that Sneakers was mimicked after, as interesting as that is as a movie. So I was definitely a big fan right away to meet him. But the whole point is where these PLCs are used, right? They're used in freshwater, wastewater. They're used in manufacturing facilities. They're used in control systems within electric utilities, and they're also used within maximum security prisons to control cell doors. And definitely a white paper to take a look at. But pointedly, it was talking about all of a sudden right before December 25th, or well, in December of last year, 2010, a maximum security prison all of a sudden had all of its cell doors opened up accidentally, which I would say is an event of interest that we would be concerned about if somebody were to get a hold of that. In further review, it was entirely accidental that it occurred. But the reality was that they were able to see security guards using the workstations that can control the actual prison to browse the internet, to watch videos on YouTube, and to read their own email on Gmail. And that just shows you right away, I mean, that's the connection or the vector of potentially a social engineering exploit to be able to gain access to the facility or be able to open up a lot of cell doors simultaneously. I'm specifically aware of a situation in a municipality police station where just the purchasing of a new copying machine that happened to have a greater amperage draw caused the circuit breakers to break open, and the PLC's configuration was that if power was lost, it would open all the cell doors. And of course they didn't know that at first. They just were wondering why in the world the cell doors opening on their own, and then they found out it happened to be every time there was a copy job that they would open up on their own because the too much draw on the panel, the electrical panel. So that moves into the actual hands-on environment that we were able to represent to our students for them to be able to take home literally an HMI or an OPC server, OLE for process control server, and a controller. Right now I have students that are wheeling around portable kits, one that's coupled up with a little Rockwell Micrologix 1100, and the other one that has a Siemens S7 1200 series PLC. And they're looking for vulnerabilities, implementation, as well as potential new vulnerabilities within the operating system itself. My goal for the facilitation of the class is not to find actual vulnerabilities in the OS or in the platform. The reason being why the Micrologix 1100 was selected is because vulnerabilities had already been identified. And the same thing holds true for us now introducing the Siemens S7 1200. Thankfully, or nicely enough, NSS Labs and Dylan came out at Black Hat and actually released some of the vulnerabilities there. I actually knew that those were coming well in advance because we actually procured our hardware from the same vendor, and that distributor had tipped me off that another cybersecurity company was doing some similar research. But what the students were able to find was a simple ping command crafted. So all 8 of my groups, actually every group I've had since forming the class has been able to do denial of service against these controllers, forcing it to no longer process its ladder logic. 3 out of 8 of the groups have actually been able to narrow it down to the simple ping command before I made this public to the other groups. And it was doing an ICMP echo request with a full payload size. And then being able to change the time increment between each ICMP echo request to be very narrow, and it would totally do a denial of service against the controller. Point being, it's very easy to do denial of service attacks. It has been for decades, specifically in any space. The other attack vector that one of my students identified was specifically just using the administration software itself and forcing a bit flip, causing the PLC to go in a fault mode. And where this becomes most interesting is that you do this bit flip using Ethernet. So what that means is an attack vector is all you have to do is record that session of flipping the bit on this controller, save it off, and then essentially you can impact any controller that doesn't have additional programming to manage this runtime fault. And then it really depends on the environment whether it be vulnerable to this attack or not. But the reality is it's a simple bit flip that you can do this type of administration on a system. And then the question is there a password on this controller or not? And then are there ways that default passwords or statically programmed passwords are no longer within the firmware? I mean, as we saw with the Siemens controller, they found a statically programmed username and password that the asset owners could not change. If you can find those, then it doesn't matter what you do as far as your own local passwords on the controllers. The next part actually is just more of these vectors and how long does it take to craft them. An example would be these man-in-the-middle attacks, creating false readings to an operator's workstations while manipulating field equipment. It took about 3 days to develop. Specifically, this attack was crafted based upon some of the students' guidance, but I actually went and developed it myself, some of the code behind it. We're going to show this as one of the demonstrations. It does use EtterCap. The reason we chose EtterCap is that it's 10-year-old technology, and again, it's readily available, and it's very, very easy to do this type of man-in-the-middle attack. Now, are there security controls at layer 1, 2, 3, and above that you can do to stop these attacks? Absolutely, and we're going to talk to those in just a moment. The reality is it only took 3 days to build it. And it really, the magic was to find a good reference environment specifically for this communication protocol. Purposely, we selected Allen Bradley's PCCC protocol because it's not as widely implemented as other protocols like Modbus or DMP3. But those protocols can be attacked actually even easier than Allen Bradley PCCC because of how much information is already out there. So we purposely selected a certain protocol because I just don't want in the wild this type of attack to be out there against a more commonly implemented protocol. Another attack was actually doing a hardware physical cyber attack, is essentially a USB mouse that has been modified to include another piece of additional hardware that makes the mouse act like a mouse and a keyboard simultaneously. We're going to be showing that again today, how this attack works. It took 1 week to build the mouse and the code to support it, but essentially it swaps out HMI tags within either an OPC or an HMI system, so now the operator is looking at the wrong points out in the field, of course then getting the wrong understanding of what's happening. The point of this attack was actually have something similar to potentially how Stuxnet could have been deployed into an environment. Not to say that Stuxnet directly was deployed by USB devices. I wasn't there when it was deployed, so I don't know how exactly it propagated into an environment, but this is just an example using about $35 worth of hardware and a little scripting what you could do, and we'll show that as an example attack here momentarily. Another research, of course, is the denial of service. That took about 1 day just to figure out that ping command. That's been validated. So I'm not going to go through these in sufficient detail. There's a lot more information available in the white paper that talks about what we're trying to accomplish here. But what we're looking at is what the vector is and what type of skill sets you would need to be able to develop this type of attack and how long it would take to develop it. And all of these are, they're not years, they're not days, or excuse me, they're not multiple months. They're 1 day, they're 1 week, and 1 month. So now there's a couple other ones we're working on right now, specifically a TCP replay attack tool. And then taking that attack and putting it into hardware using the NetDuino, which then has a network interface. So it's essentially the network version of the TCDuino, which is USB-based. There will also be more information as far as where that white paper is available at the end of this webcast. So just hang by as far as where you're going to be searching for that. So that said, I want to do some demonstrations here over the next just couple minutes. We're going to go through showing an attack against unprotected communications channels. Again, this would be an implementation vulnerability, or again, as the ICS cert now quantifies this, a feature of using control systems, because there really isn't any way to protect the communication protocols. If I can get in line, you're essentially in some serious pain if somebody has malicious intent. Unauthenticated administration, showing the actual RS Logix application. So the demonstrations here is going to show a MicroLogix 1100 platform, but we can do the same thing as any platform. So don't just pick on Rockwell. We can go pick on Siemens as well. And the reason that we pick Siemens and Allen Bradley as far as the platforms, the training kits, is that covers over 50% of the PLC space. Nicely enough, there was some research done by Sandia National Labs back in 2009 that quantified what the greatest coverage is by controllers, and that's why we picked that versus GE or Omron or other areas. And then a physical cyber attack as well. So using the mouse and the TCDuino. So let me share my desktop, and I am using a totally dedicated laptop as part of this, as part of the training environment and kit. So I'm not necessarily concerned as far as what you're going to see on my desktop. So stand by here. Okay. So you should now see the actual HMI application that's been crafted for this environment. This is what would be representing an operator's workstation. Now, in the typical environment is going to have actuators, real pumps, sensors, temperature, pressure, weight. I mean, that'll be coming in. And those sensors are the inputs that are down at the bottom of the screen. And then the lights are representing our motors, our pumps, our valves, our solenoids on the other side that would be actuating the environment. Now, I also have a camera showing the real hardware that we're using. And of course, and you can see in this environment, and we have an Allen Bradley controller. And here are the outputs. Again, this is the physical controller. And I'll actually make it light up. You should now see that. I know it's a little hard with the lighting, but the red light is indicated, which would be a motor or a pump, and now we also have the green light now indicating some actuation of a motor or pump. Just to show how this would work, this kit, we just updated this kit literally 2 weeks ago to now include real physical I/O. So here's a water pump, and I can actually plug it directly into the environment, and now you can't hear me very well because the pump's actually making some noise. But this is what I demonstrated actually at a conference last week, showing how you can attack a water tower specifically. And, in this case, I also have a little solenoid here that's being controlled. This actually attaches to a little water bottle, which acts as my water tower. One of the many examples, we've also built this kit out for power grid or smart grid demonstrations, or even railroad manipulation switching. But this now includes the ability to include physical connections or capabilities. So let me just show an example of just using RS logics to do an attack. So you can see on my screen here, this would be an administrative platform so that I can use to capture the payloads or the Ethernet communications going on between a workstation and the controller, and then potentially replay these. So what this application is right now showing is the current status of what's happening in this environment. You'll actually see that right now the green light is turned on. Expand my screen a little bit. By the green indicator within the ladder logic program. If I were to turn it off, you'll now see that it's no longer indicated as being actuated. And if I go back to the actual physical representation of what this looks like, the real live controller, you can now see the red light is turned on and the green light is turned off. I'll turn back on the green light. I come back here to the actual RS Logics application, and now you can see that green light once again has been actuated. That would be our motor that we're actually running. It's very, very simple, that faulted attack that I was talking about. It requires you to change a bit within the status file. The status file is open to any authenticated user, and again, most of the PLCs that are out there and deployed typically either use a standard password or a password that's been around for years, or maybe even no password at all. And all I would need to do is to actually go in to the Errors tab. And again, you can see on my screen here several different options, several bits that are stored within the local memory of this controller. You can also see up in the upper left-hand corner, it's in remote run state. So what that is this controller is set up. It's actually running and operating right now as we're able to change the sensors, the toggles, the push buttons, as well as the actuators, the outputs. All I would have to do is change this bit right here. And know when I'm controlling this environment, I'm controlling it over Ethernet IP right now. So all I would have to do is capture setting this 1, and immediately the environment becomes faulted. You can see in the upper left-hand corner, a fault has now been created on this controller. If I were to go back and actually look physically at the environment, there's some little lights up here. I know you can't see them, but the reality is now one of those is lit up that says I've had a runtime fault. Now I'm going to go ahead and clear out that fault, change that value back to a 0, and then to re-enable it, I need to go and clear the fault within the application and then go back to a remote run state. So right now I'm actually just in a programming state. Now this can be configured, these specifically the Allen Bradley PLCs can be configured whenever there is a fault, how it's going to respond, whether it's going to turn off certain outputs or not. It depends on how it's configured, but the reality is, if I take out a PLC, in what state was that output left in? Was it in a crank-up state? Was it in a ramp-up state? Could it actually have some kind of physical destruction come out of this if I could take out the PLC? And that really depends upon the ladder logic and how it's been programmed, how it's going to act. So let me show another example of an attack. And in this case, now you can see we're back in live, and here's my HMI operator workstation, and I'm going to do some toggle changes, and you can see the input 01 just toggled up, and my output is no longer actuated. I toggled it down. Again, the inputs are saying that there's an environmental change that has happened, a pressure change, a valve change, and then the output being actuated could be a motor. So whenever you have that red light being turned on, it could be a motor that just got actuated. So the other example of an attack that I'm now going to do is using, within this laptop, there is a virtual machine. And it's based upon Backtrack. It's been heavily modified. I didn't want to have to modify it heavily, but the reality was to do some of these attacks, it required a lot of updates. And in fact, I had to roll back from Backtrack 5 to Backtrack 4 Release 2 because Backtrack 5 wouldn't let me do man-in-the-middle attacks. There's some kind of network driver issue in the original release. I haven't tried it in the subsequent release that's come out because I've modified this so much. But what I want to show is one of the labs that's available in here, Lab 5, and essentially it's already pre-scripted to do this man-in-the-middle attack, giving false readings to the HMI. And I do it using EtterCAT. So if I go into the EtterCAT folder, I then have some shell scripts that are already programmed. There's some interesting ones in here. I'm only going to represent one of them for the purposes of this demonstration. But to do a man-in-the-middle attack with EtherCap, the first thing you have to do is set up an IP tables firewall that stops the underlying operating system from doing TCP resets. Because EtherCap is going to put itself in the middle between the PLC and the operator's workstations, and then the data is going to flow through it, and the operating system is going to say, I didn't ask for these TCP connections, and it'll try to send a reset. But we want to stop those, so essentially we have to run a shell script that sets up that firewall. Of course, here there's actual scripting behind this. I'm not going to go into a lot of detail of what that script is, so you can show I'm going to be dropping the resets. But then what I want to do is actually get in line between the HMI and the controller. And if I go back to the HMI as it is right now, you can see it's representing that the output 0/3 has been actuated. And if I actually go to the physical view of what's happening, you will see that there's a little red light that's been enabled on the controller. And again, I can change these toggles where now the green light's actuated, the red light's actuated. And in fact, if I leave it as the green, I can then go back to the HMI and see that it's representing things correctly. Well, now I'm going to go back to my attack environment that I have and just stand by here. And I'm going to type in the man-in-the-middle script, HMI on. Now, I also have to include a number. What that number is a pod number. So I ran this as a training course, and essentially I can have multiple pods in the class, and that's their IP address space that's been allocated. So it's going to go after pod 1. And what it's going to do is going to turn on all the indicators on the HMI, while out in the field, things still are operating as normal. And I can do anything that I wanted at the HMI side. This is just to show how simple the attack is. So now it launches EtherCap, and now it's actually doing some of the injections. And I've documented this script that actually goes into detail as far as what it's manipulating as the data is passing back and forth. And if I go to the HMI, you can now see all the inputs look like they're actuated, and all the inputs look like they're sensing something positively, and all the outputs look like they're now actuated. However, again, out in the field, things haven't changed. All right, we're still doing our toggles and our changing of our inputs and our sensing and our actuators that are being, in this case, our lights being enabled. But again, if we go back to the actual HMI environment, everything looks like it's on. So you would have to craft the header filter in a lot more detail to make this be representative of an environment or a specific type of an attack that you want to craft. But again, this is just showing an example of how simple this attack could really be. I'm going to go ahead and stop this EtherCap attack by hitting the Q, which will then go ahead and give the right information to the PLC and the Windows 7 laptop that I'm using here with all patches installed. And I'll just do so you can see it. I'll show you that little script that I'm running. It runs EtherCap, focusing on 2 specific nodes, .10 being the Windows laptop, .30 being the controller, the PLC, and then it runs with a very specific header filter. And the header filter essentially is going through and saying what bits I want it to flip and modify using EtherCap. So 10-year-old, actually over 10 years old is what EtherCap is, showing that if you can get a foothold into an environment, the types of attack you could perform. The final attack I want to show as an example, and then we'll go through some protective controls and then hand it off to Eric to wrap things up. But I want to show you this little mouse that's right here in the middle, and it's not connected. Of course, I had a laptop. It really would make a lot of sense for me to have a mouse connected. But this is an interesting mouse that's been modified somewhat. And by looking at it, you can't tell at all, except that I put a nice little logo on the bottom that actually says this is my modified mouse, because I have ones that are modified and ones that aren't. And if I don't open them up, I'm not going to know which is which. But what's inside here is a desoldered USB hub. That's the actual 2-port USB hub has been taken apart, and then it's been resoldered to connect to the USB mouse and a Teensy Arduino little piece of hardware that actually acts like a keyboard. So what I'm going to show you again, here's my operator's workstation. It's representing what's in the field correctly. Again, as you can see here, the green light is actuated once again. And I scripted this mouse to actually step us through the attack, so it's going to be a nice mouse versus I guess you could say, a naughty mouse. So I'm just going to plug it in. I didn't show you me plugging it in. I just did it right here. And what it does, it actually then launches, it does a Command W, and launches PowerShell. Now, nicely enough, Windows 7 actually includes in it PowerShell natively. Now, that'd be something you'd want to remove from the operating system, and specifically if you're not using it. I mean, this is true for anything in any environment. If you're not using an application or a capability, you need to remove that software. Now, what I've done here is craft a little bit of VB scripting. It's on the mouse itself as well, because it can have up to 8 gig of micro SD storage. The script has been nice and allows you to interact with it. Wait, we've already created 2 desktop shortcuts in full screen IE, as you can see in the background. So I can click OK. Oh, the HMI runtime was just terminated. What's happening is we're going now through a process that we're going to swap out the tags within the HMI to now have it give false readings. And that's exactly what just happened now. It's copied the tags from the mouse over to the HMI workstation or an OPC server. I don't care what the environment is. And now I have false readings. And now it's going to go ahead and restart the application. All this code is on the mouse. Or on the TC Arduino. And now you can still see that my green light is actuated. I can change the environment, but the reality is from the HMI, the outputs now are giving false readings. And in fact, you can even see on the HMI, as I'm changing the environment, the inputs, you can see that being represented correctly, but now the outputs are no longer being represented correctly. So what's happened? Compare the red and green light HMI indicators to the trainer indicators. The HMI tags have been altered only in the red and green light, serving as actuators. Toggle the switches and use the push button inputs. At least they still work. After reviewing, click OK. Being that this is an exercise, you know what? We've nicely scripted the mouse to then swap everything back so that it works correctly, and now it's representing the environment as it really should be, with the green light being actuated, or again, the outputs being actuated correctly again. So that's a tag swap, and that's essentially what can happen, or similar, you could say, what Stuxnet did. And this was about a week's worth of work. The greatest amount of time from my standpoint was ordering a desoldering rework kit and actually getting better soldering skills, being that I hadn't been using some of my engineering discipline for a while. So those are the demonstrations that I wanted to show. Give me just a moment here. I need to remember how to get rid of my full screen IE. Nicely, it tells me how to do that. And we'll go back to the presentation. So let me turn off my desktop sharing. All right, and let me summarize some of the security controls that we recommend, and recognize that there are lots of controls that you need to do for an environment. But these are the basics that you need to go through, and a lot of this from the NERC SIPness that is out there that we've had to deal with specifically for electric utilities. I mean, baseline your environment. Baseline what in the world you have. Find every system, every node, how it's configured, who administrates it, where the passwords are. I mean, you have to understand what you have. This goes back to the Sun Tzu comments of eons ago, right? Perform segmentation of your control system environment, and not only segmenting from your business network, but also segmentation even in the environment, let's say for the safety systems to the rest of the environment. And when you combine the baselining, even of what's programmed, you have to find out the ladder logics there. You need to look at detail of how the ladder logic is even crafted. What happens if a sensor goes away? If a sensor goes away, all of a sudden does a water tower drop its, does it release all the water, not creating a flood? I mean, do a search for computer glitch water, and you're going to find some real situations, Bartlett, Tennessee, Cedar Falls, all of these things that have been happening in these environments that have created pretty massive, not casualties, but a loss of a water supply. And then you go back to the EPA's training, which then talks about, what if you create a fire at the same time that you then drop the water tower levels. And those are details that are in that training environment. Great training, but I don't think it should be publicly accessible. And then enabling your security information event management solution. Once you have a good baseline of what you have, once you have proper segmentation, which thereby is saying that you have some controls in place, now you need to get the information from those controls. Who is authenticated using what, to what node, who just accessed some physical panel or the guard gate, who just made a modification within the environment. All of that should be coming into that SIM system so you can do analysis. And then ultimately, you need to have defined incident response capability, because if you don't have that, then your SIM system really is really useless from that standpoint, because you're not going to know what you're going to do when you see something. If you just watch, oh, hey, I'm being attacked, what do I do now? I mean, you have to do something about it. I mean, ultimately, security fails if there's no response. Security is about having good response. Security is understanding your current state of mind and current state of the environment. I mean, that's where once you do the baselining, once you do the segmentation and have the controls in place, you have to have something that can centralize those notifications, and that's the power of a good SIM solution. And it has to include details from operations, physical security, and cybersecurity. You have to have that type of joint awareness across them, and then have a good incident response capability. So, that said, I want to hand things over to Eric, who's going to, from Nitro, who's going to talk about some of their solutions.
Great, thank you, Matthew. As always, excellent work, and it's a pleasure to be working with you. This type of research is incredibly valuable. As a representative of a cybersecurity product vendor, I have seen firsthand in many cases that the work that we do is much easier when there's work being done by educational and academic institutes such as the DePaul effort and other efforts similar to it. Ultimately, nobody can work to stop vulnerabilities, whether within an operating system or an application or within a configuration type environment like we've seen here. You can't stop the vulnerability unless you're aware of it in many cases, or it's certainly a lot easier to stop it if you're aware of it. So, so my hat is off to you, Matthew. I also want to thank everyone for attending. I'm going to keep my section relatively short. We are running a little late on time, and I want to leave room for questions. What I'm going to talk about today is primarily about 2 of those 4 recommendations that Matthew just made. I think when it comes to security controls, firewalls and intrusion prevention systems and network access control and those types of things are very easy to understand why you need to put those in place. And incident response, similarly, is easy to comprehend. But I often get questions about, why is this baselining effort really necessary? And why is active or automated monitoring necessary? I get these 2 questions a lot, I think because they're difficult. And for pure compliance standpoints, I don't want to say anything negative about the efforts behind the NERC SIP compliance efforts. But if you look at security purely from a compliance standpoint, monitoring isn't an active process, it's a archival process, right? So you're collecting logs for an audit trail. But if you do baseline activity and you do monitor in an active or automated facility, there are a lot of things that you can do to stop the types of available attacks like we just saw. Once you know what to expect, you can easily detect the variations in that expected behavior, and it's those variations that are the key indicator to a lot of threats in these environments. The however is that baselining behavior isn't easy, especially in a real-time environment. Depending on the specific control system environment, however, that process may be well defined. Typically, a production line won't change terribly often, and if it does, it will change between, set manufacturing builds, or a particular product will run on a line, and then a new product will be switched to that line. In the more critical infrastructures, when we get into energy, electrical generation, nuclear generation, there's less variation there, and those processes tend to be extremely well defined. And because of that, then baselining that behavior can be a little bit easier. There's also a little bit of a gotcha in that sometimes monitoring control systems can be difficult in and of themselves. A lot of industrial control system devices, such as PLCs, don't necessarily produce logs. That is changing, or has the potential to change at least, in that the devices themselves are getting smarter. There's still a reluctance in the industry in large to put a lot of host-based security controls and logging mechanisms within these devices, because it is a real-time environment, and every process is a potential impact to that real-time environment, which would then ultimately impact the process. So it's not easy, but baselining and monitoring can be done, and when we do them correctly, we can gain a lot out of it. So I am a vendor, so I have to give the blatant plug. the Nitrosecurity and Nitrosecurity product, which is a SIEM, security information and event management system, has some capability to help automate that baselining capability. So the product can do some of that hard work for you. I don't want to spend a lot of your time today talking about product, but there'll be follow-ups after this. The white paper will be made available, and you'll also have the opportunity to reach out for more information from us if you'd like it. So now what I'm going to do is I'm going to walk into some specific use cases. What you can do once you have that baseline in place, once you understand your environment, and once you're monitoring the system, a SIEM can provide some great tools. The most common for threat detection is correlation. Event correlation is basically it's a larger scale pattern matching technology than what you'd see in an IDS. It's looking at lots of logs, lots of events, lots of activities throughout a system and finding patterns that together mean something a little more eventful. Now the problem with event correlation is that you need to know what you're looking for in order for the generated alert to have a whole lot of relevance. So 3 use cases I'm going to run through really quick. The first is one that uses comparative knowledge. So we know a few things based on the demonstrations we just saw. For example, we understand that the HMI is sending certain commands, right? There are buttons being pushed at the physical controller. There are also HMI commands that are being received, and they're different, right? So if we're monitoring both, if we're monitoring the actual HMI itself and the representation of that over the network, or the PLC itself rather, and the commands being sent from the HMI, and we see that they're different, that's an immediate indicator. There should be an alert that's given, and that alert should have a very high severity. Similarly, and a little bit easier to implement, is hopefully we know the source IP of the initiating interface. We know, either because we have a list of those IPs because we've done our due diligence and we've identified all of our controllers, or because there's a system that's providing a baseline indication of the expected authentications and the specific number of source IPs that those originate from. We can create a rule that says if the number of source IPs initiating commands is different from the expected number of source IPs initiating commands that we've seen, we also want to set an alert. This obviously would help detect the types of attacks we were just seeing. But the commands are either being injected in line, there's the mismatch, or there's a rogue device out there creating commands that we don't want to be on the system. Another interesting application of event correlation requires some context. This one's very simple, right? I think most cybersecurity controls at this point can detect a scan, right? An IDS can detect a scan, firewalls can detect scans, all sorts of things can detect scans because they're very, they're step 1 basically in a hack attempt. But what if there are specific characteristics that we're looking for? In this particular example, there was a scan that was intended to do denial of service. There may be very low and slow scans being implemented in order to try to successfully map out that control system environment without causing a failure, right? Because sometimes the denial of service is the intent, but sometimes actually getting the information is the intent. So if you have specific characteristics around your control system, and you say, if I detect a scan and those characteristics exist, right? It could be a characteristic of the scan itself or of the targets of the scan. Then we've created a very basic event. We've applied some context to it, and now we know that that has a lot more relevance, right? And I put 2 examples here because really any event, not just a scan, if it impacts any characteristic of an industrial control system, should have an immediately higher priority. And now I'm going to use a more complicated example. So this is the baseline anomaly example. This is a great event correlation rule that I think probably nobody would ever have thought of prior to seeing the demonstration of what I've dubbed the mouse in the middle attack. I apologize to Matthew if that's an oversimplification or an insult to your really clever hack. But we know certain things, right? We know that there are hosts out there that have IP addresses. We know that those hosts have things attached to them, such as keyboards. At least in Windows 7, if you're looking at the Windows event logs, you'll be able to see that a new keyboard has been connected. In some cases, if you've configured Windows events correctly, you can actually detect activity on that hardware. So it is possible to configure native Windows logging on most HMIs and control system devices still run on Windows. Configure the native logging of those devices to give you this type of visibility. If we get keyboard added type events from Windows in a SIM, we can create very easy rules that will say, if we see that on a particular host the number of keyboards detected is greater than the number of expected keyboards, which should be a baseline of 1, I don't know many PCs out there that have more than 1 keyboard, then issue an alert. There's no good reason why an extra keyboard should be there. You have to assume it's rogue. So with that, we're running really tight on time, so I'm going through these quickly. In summary, what we've talked about here, control systems are different and they're vulnerable. They require controls to protect. The hacks are out there are easy. Not to say that they're, not to insult the intelligence of the students, but relatively new to this industry, both security and control systems, we've seen students being able to create some pretty potentially devastating attacks. So put the controls in place and monitor it. Provide the context around your own system and learn your own system enough so that you can baseline it to create the correlation rules that will protect that system. So with that, again, I thank everyone, and I'm going to open it back up to the moderator for questions.
Thanks a lot. Now we're going to get to the Q&A portion of this webcast. If you have any questions, please type them in the chat and we'll get them answered. Thank you.
There was one question that came in. This is Matt Luallen, and I wanted to address it, and it had to do around ethical issues handled related to these research projects. For example, while pushing on a system, this is from one of the audience members, you just might cause it to not operate as expected, and this might result in human harm. And it's an excellent point, and that is why, very specifically, these training kits were built self-contained. Literally, the kit has a laptop, a controller, a network, all isolated and separated where you're not supposed to be connecting this to any other infrastructure. And let me just give you a real-world situation that happened, I don't know, a couple of years ago. We were at a facility and they went through in detail saying that we're only going to be hitting the business network. The control system environment is properly segmented, and there is nothing from the control system environment on the business network. And this is the only time that I've ever gone through the process of not personally validating every single node, every single network connection, because we were given repeated guarantees that no control system hardware was on the business network. We had them sign a waiver of liability, again, to assure that we were not going to be impacted in any way if something were to happen. And we simply just started doing a scan on the environment. And as part of a Nessus scan, once you find a node, it then goes further depending upon what additional vulnerabilities you want to test. It will then go and test those. And one of those had to do with a simple SSL request for what types of encryption and hashing algorithms the remote node supports. The administrative interfaces for a specific brand of industrial control system network switches was on the actual business network, and it then forced it to go out, and essentially visibility was lost for part of this electric utility out into the field. So, point being, you have to exercise caution, multiple layers over whenever you do anything in this environment, and for the training environment specifically, we make certain that it is entirely isolated. Very good question.
Okay, thank you very much for that. And now we have another question. How does the kit compare to the one from Tofino?
You know what? I know there are several kits that are out there. I've seen the Tofino one at the some of the actually on some of the show floors. They brought it by. So that The requirements for this kit specifically when we developed it was that we did have a commercial client that was requesting us to develop it, and they wanted to bring Idaho National Laboratory on site with their training environment. However, with the conflict of funding, where their funds were coming from, they couldn't necessarily provide commercial training on site for an organization, and secondarily, it was stated that it's going to be difficult to move all the equipment. So we had a requirement that we could fit all of our equipment within carry-on luggage, and literally it fits inside of a Pelican case. Now, I find that interesting that yesterday, actually at O'Hare, I guess a Pelican case exploded, so I don't know what was inside that. But we have our equipment within inside of a portable carry-on luggage Pelican case that I have taken on flights around the world already. You know, everything being self-contained. Included now, as of just 1 week ago, now real physical sensors, real physical hardware that we're actuating, really using a proprietary model that we're going to, we started the process of patenting.
If I could add to that as well, having used both kits, there's a fundamental difference, I think, between the purpose of the kit. Ultimately, they're a PLC and they're an HMI to control that PLC, and with scripted attacks to run against them. The Tofino kit is more, I was going to say, in its default state, is designed to highlight the capabilities of the security controls that you put in place between them to stop those attacks rather than to prove the vulnerabilities in the attacks themselves. So there's a little bit of a fundamental shift there. We mentioned that the security controls are important, and if you put the right security controls in place, in an industrial control firewall right in front of the PLC, certainly a fantastic way to stop an attack on a PLC. I also wanted to make a comment on the earlier question as well. The question of the ethics behind this type of research in general, and about the disclosure of the results of this type of research, they're certainly legitimate. From the vendor side, again, we run a threat research lab with the intent of creating controls to protect devices based on known vulnerabilities. And when the researchers and the vendors come together and work cooperatively, the risk is lowered across the board because the controls, compensating controls, become available more quickly. And then the zero-day attack becomes a no-day attack, right? Because the defenses are able to be put in place before the vulnerability is disclosed. We've seen that working directly with some of the control system vendors. If something gets announced publicly, we can do our best to plug that hole as quickly as possible. But if we work with them cooperatively in advance, the results are better across the board. So I just wanted to put that out there as well.
Okay, thanks. And then last question we have here. It seems like a lot of this is a matter of education. Control system operators aren't used to having to deal with this type of outside attacks. Eric, what type of education points are most important to system operators and security in these environments?
That's a very difficult question to answer because it's an absolutely true statement. There are two worlds that are colliding. The Seinfeld fans out there will recognize my George Costanza-ism. But I think the most important thing to understand is that the typical IT environment, the enterprise networking environment, and the control system environment are connected. They are interdependent upon each other. The air gap between them is mythical at best. And so the awareness that aberrations or faults within an operational process could be originating from the industrial protocols, from the network behind it all. It seems like something very simple, but it's difficult to overcome when you're not used to thinking that way. Ultimately, the way to achieve that is to have those two groups working together very cooperatively. And again, that's something I don't see as often as I like. In terms of deeper education than that, it is a very complex subject. So there is a lot of education that's required. Luckily, through SANS and other organizations, the information needed is getting out there.
Okay, thanks a lot. And thank you so much, Matthew and Eric, for your presentation. A special thanks to Nitrosecurity for sponsoring this event and bringing the content to the SANS community. To our audience, we really appreciate you listening in. The associated white paper will be sent out to everybody after the webcast, and if you're listening to the recording and have any questions, please send them to q@sans.org. For a schedule of all upcoming and archived webcasts, please visit sans.org/webcast. Until next time, take care, and we hope to have you back for the next SANS webcast.